Welcome to The Explainer. Today, we're diving into one of the biggest, thorniest challenges in AI. How do you make these models unbelievably powerful without giving up our personal privacy? It really is a paradox, a delicate balancing act, and some new research is finally giving us a clear blueprint for how to solve it. And this quote from the research paper that inspired this whole explainer, well, it just sums up the problem perfectly. It says direct training on sensitive user data is risky due to memorization and regurgitation. In other words, the model can accidentally spit back out the private stuff it learned. I mean, that's the fundamental tension we're dealing with in AI development today. So it really makes you stop and ask a pretty critical question for all of us. Does your AI actually keep secrets? Like, really? How do we get all the incredible benefits of AI, which, let's be honest, comes from it learning on our data, without taking this huge risk of our most sensitive info getting out there? Okay, to really get a handle on the risk here, we gotta look at how these models get so smart in the first place. You know, these large language models, LLMs, they're trained on these just unbelievably huge data sets. We're talking trillions of words and pieces of data scraped from all over the internet. And the thing is, that data isn't always cleaned up or anonymous. It's full of personal stuff that people shared, maybe without even thinking about it. And that's where we run into what you could call the AI's memory problem. See, the huge issue is that these LLMs, they can actually memorize parts of that training data. And yeah, that includes the sensitive stuff, names, phone numbers, you name it. And studies have shown again and again that the model can just accidentally spit that information back out in its answers. This is a huge privacy nightmare, especially for these open-weight models that anyone can just download and start digging into, trying to find those little memorized secrets. So how on earth do you solve something like that? I mean, how do you build an AI that has amnesia for all the personal details, but still remembers all the useful, general knowledge it's supposed to know? Well, researchers are turning to this really powerful mathematical concept that basically acts like a privacy shield for the data.
And that idea is called differential privacy, or DP for short. Now, this is considered the absolute gold standard for privacy for a reason. It's not just some nice idea or a loose guideline. It's a super rigorous mathematical framework. What it does is give you a provable guarantee that any single person's data has a very, very limited influence on the final model. Basically, the model's answers will be almost exactly the same whether your personal data was used to train it or not. Your privacy is literally protected by math.
So how does this mathematical shield actually work when you're training a model? Well, it's usually done with a process called DPSGD. Let's break it down into 3 simple steps. First, for any piece of data, the system figures out how much it would change the model's mind. Second, it clips that change, basically putting a hard limit on how much influence any single person's data can have. And then, the secret sauce. It adds just the right amount of mathematical noise. Think of it like a statistical fog that hides individual details but keeps the important general patterns visible. Okay, this sounds pretty great, doesn't it? A mathematical guarantee of privacy? Seems like a no-brainer. So what's the catch? Why isn't every single AI model on the planet built this way? Well, here's the problem. Adding that privacy shield, it kind of breaks the traditional rulebook for building powerful AI. See, applying differential privacy completely changes the game. It changes the fundamental dynamics of how these models learn.
And this is where you can really see that core conflict laid out. The standard AI rulebook, the one everyone's been using for years, is pretty simple. Bigger model, more data, better performance. It's predictable. It just works. But the moment you add differential privacy, that whole rulebook gets thrown right out the window. Suddenly, a bigger model with more data can lead to total training chaos. Things get unstable, the results are unpredictable, and it just costs a fortune in computing power. The old rules, the old scaling laws, they just don't work anymore.
So for years, this was a massive roadblock. It meant that any model built with privacy in mind had to be way, way smaller and just less capable. I mean, we're talking models with a few 100 million parameters, while the big, state-of-the-art models were cruising past with tens, even hundreds of billions. It was a completely different league. That is, until now.
So what was the big breakthrough? Well, researchers finally realized they had to stop trying to force the old rules to work. They needed to throw out that old rulebook completely and write a brand new one, from scratch, specifically for training private AI. They needed new scaling laws.
And this chart shows one of the first really fascinating new rules they discovered. It's totally counterintuitive. For the same amount of computing power, the best private model is actually way, way smaller than the best non-private one.
So if you have a huge compute budget, the standard approach says build a 10 billion parameter model. But the new private rulebook says, nope, you're better off with a much smaller model, around 100 million parameters. It's a completely different strategy. So you're probably wondering, how do you make up for having a smaller model and all that extra noise from the privacy math? Well, the new blueprint has an answer for that too. You train with way, way bigger batches of data. It's just a totally different recipe for what makes a successful model. And here's the crucial takeaway from all this. We finally have a reliable map, a real blueprint. These new scaling laws give us a guide for building powerful private AI without just guessing. It tells us exactly how to balance all the knobs, model size, batch size, compute power, to get the utility we need for the level of privacy we want. So, armed with this brand new blueprint, researchers at Google went ahead and built something to prove it works. They created VaultGemma. It's a 1 billion parameter model that puts all these new rules into practice, and it's now the most capable, openly released differentially private language model out there. All right, so how does it actually stack up? This table is super interesting. Now, you can see there's still a performance gap compared to a modern, non-private model of the same size. But look at this. VaultGemma's performance on these benchmarks is pretty much on par with a powerhouse model like GPT-2 from just a few years back. So it shows just how far we've come, but it also gives us a real number for the cost of privacy today. And here's the proof in the pudding. It's formal privacy credentials. It offers something called sequence-level privacy. What that means is that it protects any chunk of about 750 words from the training data. The really important number here is the privacy budget, called epsilon. Just think of it like this. The lower the number, the less privacy is lost, so the better it is. A value of 2.0, like we see here, is considered a really strong mathematical lock against the model memorizing things. But honestly, the most stunning result of the whole thing might just be this. The researchers really put it to the test. They tried to get it to spit out training data, and they found 0 detectable instances of memorization. Let me say that again, 0. It's proof that this privacy shield really, really works. So what's the big takeaway here? What does this all mean? Look, this is way more than just some academic exercise. This is a huge foundational step towards building AI that we can actually trust. Trust with the important stuff, in healthcare, in finance, with our own personal data. For the first time, we have a clear path to get there. This kind of breakthrough really opens up a whole new frontier for developing AI. And it leaves us with one last really important question to think about. Now that we actually have the blueprint for building powerful and private AI, where should we start? Where do we need it most? Thanks for joining this explainer.